Alright, so here's part 2 of section 1 on studying language. And so let's get back into psycholinguistics and sort of the history of psycholinguistics. So if I ask you to name someone who comes to mind when you talk about studying language, most people say Chomsky. And that is a great thing. He's probably one of the most famous psycholinguistics people, but he's certainly not the only one. So let's look at sort of the history of psycholinguistics. Very brief, very short history of the study of language itself. So in the 1900s, Galton really started this, but he was more studying intelligence, but he was looking at word associations. So if I say cat, you say mouse, or cat, dog. And word associations have a storied history that have kind of been used throughout the years in different ways for different things, but it is a study of language. He also studied slips of the tongue. So when we get into a little bit of Freud, not a whole lot of Freud, but he was really studying that idea of Freudian slips, that error that people make when they're saying one thing, you mean something else, or where you get stuck, so sort of speed errors when we're going too quickly. But psycholinguistics didn't really catch speed till the 1950s, and that's about the same time that cognition really became its own section of psychology. And so that happened at Cornell. It was the first time something was described as a psycholinguistics conference. 1956 is the year that we have our first sort of big cognition conference. So the 50s is kind of where we really get started in the way that we know psycholinguistics today. But if you ask people where did language start, most people sort of start with Chomsky and move forward. Even though Chomsky's certainly not the first one, he's kind of the one that revolutionized the field. So he was publishing papers on language, what he called transformational grammar. So this idea that language is innate and it's built in and it's really a reaction to behaviorism that was controlling psychology at the time. But I don't recommend reading Chomsky because, it is dense. If you want to be convinced that language is totally innate, which is not true, but you should read Steven Pinker's Language Instinct. It is very readable. He has fantastic writing, and that man could sell you water in the ocean because he is a very good writer. And he writes about a lot of interesting things. And there are some criticisms of his writing, but I think it's a great book and it's really interesting. But Pinker comes along a little bit later. In the 1960s, Chomsky and Skinner sort of famously had a bunch of publications back and forth where they argued over this idea of innatism in language. So Skinner's book was called Verbal Behavior. It's this idea that language is totally learned, and it's all a stimulus response thing. So it's all behaviorism. So it's all that learning stuff. Chomsky lit him alive because he thought there's no way it can be learned that way. There's just you're totally wrong and incorrect. And they kind of went back and forth over it's innate, it's not innate, it's nature, it's nurture, it's nature, it's nurture. And Chomsky was really trying to show that behaviorism doesn't cover all of it, but I don't think that genetics covers all of it either. So really is probably a blend somewhere in the middle, and we'll get to that a little bit later. But this is sort of what started that conversation, where it really was a typed shouting match. In the 1970s, once cognition really hit its stride, language was viewed more as a cognitive processing approach, so information processing. And now, where we really do is really focus on models of language and understanding and processing for language. And so you will get straight up sick of all these different boxology models, is what they're called, where we're looking at, this one isn't language based, but it's this idea that there are processes that lead to other processes. And so we're really moving beyond is it nature, is it nurture, into how do all these different components of language interact, and how can we build a comprehensive picture of language and the individual. Okay. So linguistics versus psychology. So the old linguistics, or more traditional linguistics, sometimes called comparative linguistics, is tracing the origin of these different languages. So we're studying their structure, their syntax, and discovering languages, and really seeing like how those languages branch off of each other. So how do we get Spanish and Portuguese? How do we get two different forms of Chinese languages? How do we have some languages that are symbol-based and some that are letter-based? Still cat here, because he's not getting my language. The cats are not allowed. All right. The new linguistics is studying more of what is and isn't acceptable in a sentence. So what is valid language versus what do people understand kind of right away? So how do children understand different components of language? And still arguing about nature versus nurture and really trying to suss out that in a more descriptive way than sort of a big overall argument. You're annoying. You can tell it's almost dinner time. All right. So for psychology, the way we treat language is that humans are processors of language, and the focus now really is on information theory. So it emphasizes that language is probabilistic. So some words are more frequent than others, and word frequency. If you don't know the answer to something, guess word frequency. So language is statistical in a sense, so that's one reason why I like it. And it's redundant, so we have a lot of words that mean the same thing, and a lot of the same similar structures, and we use that redundancy to our advantage. So we know we tend to do noun, verb, noun, where do adjectives go, where do adverbs go. So if you give people, I went to the bank to deposit my, and you ask them what word should come next, we're going to use frequency and meaning and our understanding of those probabilities to come up usually with check or money, because that's probably the most likely suspect of the different words that can go there. So it's still really important to study these things today. Expectancy, word expectancy, and word frequency are the strongest predictors of different things in language, including Alzheimer's and dyslexia. If we look at the behaviorism route, so more of the Skinner idea, what we're looking at is stimulus for S, response for our pathways. So if you say something to me, that is a stimulus, and then a response comes out. That's a little too simplistic, I think, because language is so complex. And then there's also conditioning, so how we teach people how to say language. So if you are in any of those communication science classes, give me just a second. Come on, cat, go away. Good gracious. Communication science classes or any of the ABA stuff, you're taught a lot of this sort of thing to help fix problems with language. So like autism or dyslexia, speech pathology really focuses on training people how to say words better, or there's lots of things, but that's just an example. And that is very behavioristic because that helps us fine-tune language. So it might be that language is a lot innate, but then behaviorism really allows us to structure that language. And that's a really popular idea because you can see it as moms talk to their children, so sometimes called motherese. And just in general, if your friend mispronounces something, you'll laugh and tell them the way to pronounce it correctly, and that's a very stimulus response kind of interaction. But something new and sort of interesting is this idea of artificial intelligence. So artificial intelligence, and this is from the Terminator TV show, is a tricky thing to talk about for language because it's an ultimate goal that I don't know that we'll ever get to. So there's a lot of research that tries to program computers to think about language the way that we do, in this idea that if we can get computers to process language the way we do, a lot of tasks will be simpler, and we'll be able to have smart machines. But anyone who's interacted with Siri for more than an hour has realized that doesn't always work. And that is a really good example of an artificial intelligence machine. And, it has its quirks and its moments, especially if you try to do talk to text, where you're like talking, telling it what to text your friend, and then you look at what you actually texted them and you're like, oh my God, what the hell? So success in this area is pretty limited. So there are some examples from literature, from like research literature that aren't Siri. So it's Eliza, Perry, and then the last one you can't pronounce clearly. There's tons of examples from TV and movies. So she's a robot in the Terminator Chronicles. And I don't know that we'll ever get to that point. There's also the newest thing that's most exciting is IBM's Watson. And so that is an artificial intelligence machine that tries to think about language the way we do. And it has some funny quirks with it, but it's sort of an interesting development because it's sometimes childlike, but it seems to be working a little better than some of these other artificial intelligence machines. Siri is also a great example. And so one thing that really brings up is this idea called connectionism. So connectionism, sometimes called neural networking or parallel distributed processing. And so it's this idea of a brain being a computer. And computer simulations really try to build models that aren't boxology, from the previous lecture, that are connectionist, because they're trying to mimic the neurons in our brain. And so we sort of build these little models with all these different nodules that sort of map onto neurons that learn statistical regularities. So let's see if I have a picture. I don't think I have a picture just yet of them, but they're sometimes called bubble models because they look like little bubbles. And the idea is to mimic neural messaging in the brain by programming in a computer in a parallel distributed way. So why parallel? Parallel means doing several things at the same time because your brain is doing a lot of things at once. It does not tend to be super serial where you're doing things not breakfast cereal as in one at a time. We tend to do lots of brain processes at once. Neurons clearly are the way the brain works. And so connectionism, which we'll spend a lot of time talking about this semester, is this idea of programming language and understanding language like it works in the brain instead of using these box models. Okay. Activation is this idea of how much energy I need to do something. So if you have had a physio class, it's sort of like how much stimulation a neuron needs to fire so that an activity happens in your brain. But really, we're going to get into spreading activation. This is really important for priming, which we'll get to in a second. It's just this idea of like, this thing activates the next thing, which activates the next thing. So sort of like dominoes. So the neural firing spreads as if you've spilled water or knocked over the dominoes. So some ways to study language in general, this is sort of overall. So we can do that computer modeling we were just talking about with sort of doing artificial intelligence. We can just straight up observe people. We can ask them their thoughts and feelings about language. Or we can program experiments. And so one of the biggest things we'll do this semester is talk about priming, because priming is one of the main experimental designs for a lot of studies of syntax, semantics, and phonemes and morphemes. And so priming, what that is that you have this cue word. So let's say I said cat, and then a target word, which would be a related word, dog. And so that target word, the second thing, is faster or processed somehow differently because of the first thing. So when your friend's coming to me like, remember that thing I told you the other day? That would be the prime. And so the thing that they're about to tell you gets processed faster because they reminded you first. And so priming is sort of like a little reminder. It's like, oh yeah, don't forget this thing. And so then the thing you're actually trying to process gets processed faster. It can help or hurt you. Priming can actually make you go slower on some things because you can get stuck on an answer you thought was right, but it's not where they were going. But mostly it helps you by helping you process things quicker. Because if anything is true about the brain, it is lazy and it likes things to be processed easily. It likes new things and things to be processed quickly. So anything we can do to make shortcuts, your brain will do. So with experimental design, we can study semantic priming. So that's word-related priming. There's also orthographic priming, which is like how things look. So sort of picture-related priming. So our second word, dog, is processed faster, cat, because then if you preceded it with another word, so let's say we did doctor, dog, dog would be kind of slow. If we did cat, dog, dog would be faster because cat sort of got you thinking about dog first. And the way we study that is through response times, sometimes called response latencies, reaction times, reaction latencies. There's lots of different words for this. And then some really common variable to measure is like how fast people are doing things. Another variable you can measure is how many times somebody gets something right, or there's just the frequency of the different answers. So I went to the bank to deposit how often does the word check come out? So those are probabilities. The other way we can do this is study the brain. So if I look, just a very quick, brief overview of some physio stuff. And so one interesting thing is we can do lesion studies and brain research on language. This is where it started because we just didn't have the technology before to really study language in the brain the way we do now. So when people had language problems, we just had to wait till they were dead and then cut open their brains. So how does brain damage affect performance? Now we can take stroke victims and study them because we have a way to look in their brain. So this is really one of the only ways to study brain functions. And so some of the areas associated with language, so I have a picture here, that's Broca's area. Broca's is here in the front. We'll talk about these a lot, so you don't need to write this down yet. Wernicke's is here in the back. And those are two areas that are very specific language structures, but you also have a whole lot of language that goes on in the temporal lobes and temporal and parietal lobes. Anything that is visual occurs in the back of the brain, the occipital lobe. So language, while it has some very specific areas, really could not function without a lot of the rest of the brain. Because even people who are blind still have activation in their occipital lobe for pieces of language that would be visual. So one problem with all this research on lesion studies is it really focuses on where things happen in the brain and not why. So it focuses on like, yes, this is Broca's, that's great, but how's that Broca's related to everything else? And why does Broca's work the way it does? So why here in the front? And what does it actually do? So it focuses on the where and not so much the rest of it. And so one thing we can do is what's called a double dissociation. And this is a little tricky. So it's a pattern result. So let's say we have two different patients where one of them can do one experimental task and another one can do a different experimental task, and then vice versa. So patient 1 can do semantic priming, whereas patient 2 cannot. And then patient 2 can do orthographic priming, which is more visual and not meaning-based, and patient 1 cannot. That is a perfect world, because if you have those sorts of things where you can do one thing but not another, and someone has the exact opposite effect, the different areas of the brain that are broken, so to speak, that tells us where those things happen and the sort of what that goes with it. Those never happen. Very rarely do they happen. And so we tend to get these mixed effects that are sort of difficult to interpret. But that would be a perfect situation for pulling experimental research together with lesion studies. Now what we can do is neuroimaging, so we can take the brain while processing is happening and not just after death, and look at, in real time often too, what the brain is doing. The problem with this is it's very, very expensive. There are two main methods. There's a couple more, but the main ones that we're going to cover are EEG, which is very good at timing, and then FMRI, which is very good at placement. And so getting both time and place requires some systems that are prohibitively expensive. And then some of the issues with subtraction rules. So subtraction rules are this idea that if I take a fMRI picture of something and you're just sitting there breathing, your brain is doing a lot. And you're thinking, right? So you're still doing language. And then they ask you to do something and they subtract those two pictures. Should we do that? Should we not do that? I mean, if you're just laying there thinking about how loud the damn machine is, because fMRIs are pretty loud, or standing, they have the new standing ones, those are cool. Should we exclude that thinking. Should we not exclude it? Yes, it's not what I was asking you to do per se, but you're still thinking and there's still language going on. So subtraction rules get kind of tricky when we talk about language. So, well, you guys have gotten a CAT scan throughout both of these lectures because CAT has been very needy today. But we'll get CAT scans, PET scans, MRIs, optical imaging, some EEG, ERP, and some transcranial magnetic stimulation. So let's talk about each of these very briefly. Okay. So CAT scans and PET scans are some of the original sort of imaging technology. PET scans are when they would inject you with a radioactive dye and then use the decay of those isotopes to take pictures of the brain. So here's what it looks like, a weather map. So red areas are processing more information. So got lots of occipital lobes, so visual stimuli going on. But here's Broca's here in the front, so these two little pieces, and Wernicke's here in the back. And so we were able to see what parts of the brain were lighting up. So which sections were currently being used. FMRIs, or functional magnetic resonance images, are the newer version of those. So people don't got to be injected with dye, but you can't have they are giant magnets, so you can't have any metal parts and go in one. And then you can't, they are very loud, and in general, if you are in one of the lay down ones, they're very small, so people can be claustrophobic in them. But they're much better at giving you these slices of the brain, and so they give you a very good picture of where something's happening. So this might be Wernicke's back here. To me, the real action on timing in the brains. So we process language at an unbelievable speed. You can listen to about 15 words per minute and still understand, not words per minute, per second, sorry, and still understand, 15 words a minute would be really slow, 15 words a second and still understand what's going on, which has been really helpful for me here where everybody talks really fast and I'm from the South and everybody talks really slow. And so we can process at an unbelievable speed. And so this technology, while it's really good at wear, so here's the other cat. It's cat day. You guys all super lucky. Here, come sit. Nope, just get out of the way. There you go. All right, so the problem with the imaging technology is that it gives you a picture of wear, but not very quickly. So these slices take time to load and they take time to scan. And by that time, language has come and gone. The EEG, so an electroencephalogram, or an ERP, an event-related potential, as part of the EEG, is where I can really get at the timing. And we can kind of get a little bit of wear. People tend to wear bit caps of these, so I can say if it's in the front or the back, but not as specific as the imaging technology. But EEGs allow me to look at the speed of language. So for one thing we'll talk about a lot is the N400, which I have a picture of here. And so N400 we think is one of the times that you access language. So the N200 here, the negative one, is where I'm sorry, this is the N200, this is a reverse graph. Is where I'm sort of saying, look, it's a word, right? But the N400 is like, oh, that word is cat. We'll talk a lot about N400. It's really interesting because it allows us to see kind of how quickly people are processing words and then like how they're activating their mental lexicon to get at those words. And then we can look at an N400 and I can tell you whether or not that word was expected. And so if the N400 is really small, that was something you were expecting to hear. If the N400 is really large, it's something you weren't expecting, which is really cool. All right, so, and I don't have any pictures of these. So let me go back and make sure I cover everything. Optical imaging is a newer version of fMRIs that will use lasers to measure instead of magnets. So the magnetic machines use the blood. Your oxygen is it's not magnetized like magneto, but this idea that I can use the way that oxygen electrons and stuff work to measure different blood flows. Optical imaging does that same idea, but with lasers, and so it's much quicker. And so it's a kind of a compromise between the two, so I can still get space well and time. Transcranial magnetic stimulation is like putting a magnet to the brain, so it's a way to study lesions without busting people's brains and cutting them open, because people don't like that so much. So the way that works is they basically hold a magnet to your head, and like I said, we're slightly magnetic. They scramble your brain for a little while, and then they see what happens. So it's not something people like to do because it's unpleasant. But to sum all of this up, these two cat lectures is the goals of psycholinguistics. So what's the purpose of this class? Not even this class, but like the field. It's to understand that processing involved in producing, so the way that language is spoken, and understanding, comprehension. How are all these language processes related to each other? So how are phonemes important for understanding language, and how do we process those and then spit them back out so effortlessly? And so one thing we'll talk about is when language breaks, because that really gives us a big insight into how we process naturally. So when language becomes effortful, it's really, it's unfortunate, but it's a good way to understand the effortlessness of normal language. A little bit on modularity. So how, for each of these processes, is that a language-specific process, which implies that language is innate and built in, or is that a general cognitive process, the way that just like brain, it's not hardwired for language, it just happens to be the way we're using our brain. And so that's the idea of modularity, that are there specific modules, like there's a language section of the brain, there kind of is, or is that just because the brain is a processor of information? Okay. We will get into nature versus nurture and animal language, so which one's correct? I've already kind of talked about that, giving you a preview, and bilingualism. So looking at how people process when they speak two or more languages, so multilingualism, and how that works in the brain. Okay. And so all that taken together is the first week of studying language.